Welcome to the third New South Wales Science and Research Breakfast Seminar for 2021, unfortunately brought to you via live stream rather than in person due to the Greater Sydney's current lockdown. I want to begin by paying my respects to the Indigenous peoples of the nation on which we're all located today, and pay my respects to their leaders past, present and emerging. Just a short note, you may submit questions to the speaker via the chat function on the right-hand side of the screen, and time permitting, these will be asked at the end of the seminar. I'm delighted that today's speaker is Professor Francois Aguey-Zinsou, who leads the Material Energy Research Laboratory in Nanoscale, or MERLIN, within the School of Chemical Engineering at UNSW in Sydney. Francois is an expert in hydrogen technologies, an area of considerable focus for my office. We work closely with his colleague, Professor Rosa Mal, who is co-director of the ARC Training Centre for Hydrogen and Global H2E, which the New South Wales Government is supporting through the Research Attraction and Acceleration Program. We have a number of other programs we're also supporting in this related hydrogen and chemistry area. Francois' work at Merlin is exploring hydrogen storage technologies. In this seminar, Francois will explain the advancements necessary to enable the widespread use of hydrogen as an energy carrier, and how our expertise and ability to retain technological sovereignty in this rapidly evolving space might impact on the future of Australia. He is also developing technologies for enabling novel fuel cells and electrolyser architectures and advanced catalysts for hydrogen combustion. Francois is Vice President of the Australian-French Association for Research and Innovation, which promotes cooperative research efforts between the two nations. He is also co-director of the Australian-French Research Network, FACES, and the co-founder and CTO of several startups, as well as chief investigator of High Supply. You can see Francois is not only working in an area of considerable interest, but he is an entrepreneur and is really taking research out to the commercial world, something that we are very active in supporting in my office. Please join me in welcoming Francois as he presents hydrogen science and the future of Australia.
Thank you very much, Hugh, for the kind introduction and kind words. It's a very great pleasure to be here this morning. A pity that I cannot see you all, and it's a great honor to speak at the New South Wales Chief Scientist Breakfast Seminar. I'm going to start my talk. Let me find out how I share my screen again. Here we go. I think this should function now. I'm going to start my talk. This introduction, and when I was invited to give a talk, I thought, what are really the challenges we are facing in Australia in getting this hydrogen economy up and getting value for the country? And here there is a map of the globe. This is where we live. We are on a finite planet. And on the side here, you have a picture of the research we do in enabling new technology in the hydrogen space. And I will come to that image later at the end of my talk. What I would like to start with first is really talk about a bit of my background, because I always consider that history is important. This makes who we are today. So here we go. So I'm born between different cultures. I'm born in Africa. And so I'm born between France and a small country called Benin. My grandfather was a French resistant. He went to deportation camps and survived those camps. My other side of the family come from a country that was at the time called Dahomey, which was a French colony. And if you remember, not that long ago, organizing colonial exhibition, and human zoo was pretty common. And so when we think about things that are normal today, they were not that normal a long time ago. And so this means that as a society, we can evolve and we can do great things. Benin was very famous also because this was a port where you have along the slavery coast. And so we know the history behind this. If you go back to the history of Africa, actually Dahomey was one of the most influential kingdoms in Africa. And so it was very well known in Europe in particular, with the Portuguese coming early in the 17th century for its Amazon. So the king used to have a special army only made of women that were known as the Amazon for the European, or Mino for the Dahomean people. And so if you go back to Dahomey, you can visit what is remaining of the palace of Abomey, which was burned upon the loss of the last king of Dahomey against the French. The reason I mention that is because the last king of Dahomey was called Kondo. And so if you go to France, the Musée Quai Branly, you will see a statue here of representing him as a shark. And the reason he took that symbol is because he wanted to make sure that the French will not land on the coast of Dahomey. And so at the time, there was some propaganda also because the war was going on between Dahomey and France. And so a typical example is Le Petit Journal, where there was some articles about the king of Dahomey, Béhanzin, who was a bit of a difficult one and was given a hard time to the French. My name sometimes is seen as complicated, and typically there are reasons for that. I'm born as a Zinsou, and so the tradition in Dahomey is that the first kids that are born as twins cannot carry the same name. So I've got two grandfathers, one who was first born all the name of Zinsou, and the second one couldn't carry the same name, so he was called Aguey. Aguey means twin. And so to recognize the background of our family, my mother decided that I had to carry a French name, Francois, and Kondo, which comes from the last king of Benin. My grandfather was the first president of independent Dahomey for a year before a coup d'etat, and my father was among the African elite that were sent back to France to be educated. So my father actually studied political science. When he came back to his country, he wanted to develop a bank of investment for Africa and do things like macrocredit to help his country develop. But some of his classmates, when they came back to their country, organized some coup d'etat. So when the French government saw that my father had an ambition to develop a bank of investment, he was put in jail. And so this was the end of this adventure. So really what I want to say here is that I come from a family where community is important for us and what we do for the other is important. And when I thought about what I'm going to do with my career and how I'm going to use my skills to benefit the community, I came across hydrogen. If you think about the role of energy in our society, and here there is a small graph showing how our brain size evolve as we access to more energy diet rich, we were able to develop new tools, evolve through our culture, evolve through our societal rules, and so forth. And this means that energy has always been at the core of our evolution and societal development. So there is always that trend, how much energy we can access to. And so if you look at an unbounded growth model, which is a dream of the economist, so we have unlimited resources, so we can grow forever, the cost can reduce forever, and we can have access to cheaper and cheaper goods. Well, the reality is something slightly different. We are more likely to follow the same trend as laws that have been observed before, which is that we are limited by the access to resources. And probably what we are going to face is a bell-shaped growth. Before the Industrial Revolution, what we had access to is mainly slaves, and typically with an output of 100 watts, and animal power, and then renewable energy in the form of wood, for example. Then through the Industrial Revolution, we discover how to use fossil fuel in the form of coal, then oil, that is more energy dense, And typically, this has enabled us to significantly grow the Earth's population and grow the capability of our humanity. Those behavior of bell shells have been known for a little while now, since the 19th century. In particular, these models were developed by a Belgian mathematician, Pierre-Francois Verhulst, and typically he was looking at animal population. If you take some rabbit and wolf, typically the rabbit population will increase as long as they have access to food, and then the wolf population will follow the same trend, and then it will reach an optimum where all the rabbits are going to be eaten, and so the population is going to decrease. We know the same thing is happening for all resources, and this was shown by King Hubert, who managed to, with very similar model, predict the oil peak in the US. So for me, the best we can achieve, unless we find unlimited resources somewhere in the galaxy or the universe, is potentially a bounded growth. And so then the question is, how do we live in a world where we have a bounded growth? This is the world today. And to come back to my first comment about access to energy, you can look at this also through the Human Development Index. And typically here, what this map is showing you is that you have the rich countries where we are lucky, like in Australia, where we have access to a lot of goods and comfortable life. And so this enables us to have access to education, but also even control the number of kids we have. And typically, the more access we have to energy, the less kids we have. And so the big question is, how can we develop society that are more equal? Another way to look at this is that you can, for example, consider the Earth's population, the entire Earth's population, and divide the amount, for example, of electricity consumption across our planet by the number of people we have on the planet. And then you can classify that in a chart like this. And what you see is typically that the average across the world is about at 1. So we have enough people on the planet to produce the energy that we consume globally. So if all of us were slaves, we will produce enough energy to sustain our current energy consumption. And what you see is that these rely on a lot of countries where there is minimum access to energy, and a few countries where there is extensive access to energy. And so to come back to my point is, how do we balance that again? And I think this is where hydrogen has a key role to play. If you look at the different potential energy sources available, and you classify that against the output of a slave, typically for coal, you have the equivalent of 10 days of man output or woman output. For 1 kilogram of gasoline, 16 days, hydrogen, 49 days. I will comment on batteries later, but the energy density of batteries is rather low in comparison. And so for me, the key message I want to share with you today is that I believe that hydrogen, if we can do it well, has the power to reshape our society and provide equal opportunity. And this is a reason why I've been always extremely interested in developing the science behind hydrogen, because we can probably do very good things with that beyond the simple act of making money and creating jobs. Okay, so our solution is most likely back to the future with renewable energy. We know that we have plenty of renewable energy around us. And if you take, for example, the solar radiation per second, that's equivalent to a huge human output. We can run that through solar panel, and the technology exists, although we still need to improve on this technology to increase the efficiency, because the efficiency of solar panel is relatively low. And we also need to develop technology where those solar panels will be easier to recycle. So we actually can fully close the loop and create a real circular economy. Once you have this renewable energy, comes the question on how you store it. And this is where hydrogen has a key role to play. So here you have an example of what an ideal hydrogen cycle will look like, where, for example, you produce hydrogen through water electrolysis with a 70% efficiency. Then you need a method to store this hydrogen. And then once you have stored this hydrogen, you can export it, send it to various end users, distribute it, use it locally through combustion engine, because you have to remember that in our society to produce goods or to have access to various things, we need not only to generate electricity, but also we need to generate heat. And in particular for our homes, but also for many industrial applications. And this is something great with hydrogen. You can actually do both. And so this can help us to sustain our living standard and improve our living standard. In principle, this looks like something relatively simple. I think everybody agrees now is something strategic for our future. But I think maybe what is not realized yet is that behind this economy, there is also a need to secure key resources, mineral resources, renewable energy resources, talent people, and skill resources to be able to develop that full economy. And so in the execution is actually something relatively complex. And this also is not just digging a hole in the ground to extract some minerals. These rely on very advanced knowledge. So knowledge to develop, improve those technologies, to make them more efficient, to make them sustainable, so we can actually recycle them and reuse the material in those technologies to implement them back in the field. And so this means that we need to have a very coherent approach in the way we are trying to get this hydrogen economy up. And one of the things I'm very keen and I would like to see happening is that in Australia, we managed to put together what I call a national hydrogen research facility that brings the expertise together across the country and help us to build that critical mass in terms of knowledge and supporting the national effort. Okay, so what is hydrogen? Maybe I thought I'd come back to the basic. Hydrogen, let me find my pointer. Hydrogen is a very simple element. One proton charged positively, one electron. Here you have a very simplified model of what the hydrogen atom looks like, with the proton in the middle and the electron spinning around. In reality, it's a bit more complex. The electron doesn't spin around a specific orbital. You will find it in different positions, depending on time. When you take those two hydrogen atoms together, you will form a hydrogen molecule. This hydrogen molecule has no color, no odor. It doesn't exist. It exists in the atmosphere at very low concentration, particles per billions. There are some excitement those days about natural caverns that will contain some hydrogen, but this is yet to be determined. So really, if we want to have access to this hydrogen, we must produce it. To come back to hydrogen and history, hydrogen was first discovered in the 16th century, and there are some old manuscripts showing that Paracelsus actually simply putting some acid on some metal chips, typically iron, observed the evolution of a gas. He was not able to tell what that gas was about. Robert Boyle made the same information, and Henry Cavendish finally isolated the gas and called it the inflammable air. If you look in the literature, the name hydrogen will come from Antoine Lavoisier. And so very quickly after hydrogen was discovered, this was already used by engineers. And the first one to use that was Jacques Charles, a French. And he used that to fly some of the very first balloons. So this one is called a charlière, not a montgolfière, because the montgolfière rely on hot air. These rely on hydrogen. So the hydrogen was produced with what I would call today a dirty process. Typically, you take some iron chips and you pour some acid on it, and then this will evolve. This will get some hydrogen to evolve, and then you inflate your balloon. So as you know, between the French and English. So maybe the English discovered the molecule, but the French brought some elegance to it. And in particular, Lavoisier refined all the chemistry nomenclature in naming what we know today as hydrogen and oxygen and those molecules. Very quickly, as I mentioned, hydrogen has been used in various applications. So what we see today is the evolution of a lot of work that has been done in the background. The first person to use hydrogen for mobility was Antoine de Rivaz. He was a French also, a general, working as a general in the army. And he quickly realized that hydrogen was something very good. It explodes, and it does that in a clean way. And so he designed the first spark ignition engine. And on his small, what we'll call today an automobile, he had a rubber balloon in which he put some hydrogen, inflated the balloon, and this was sufficient to get this charrette to move for a few meters as you light the reaction. In 1863, Lenoir, who was working on developing a hypomobile, actually produced hydrogen through electrolysis, and then he had some storage vessel on board and ran this hypomobile in Paris, between the middle of Paris to Joinville-le-Pont at a speed of 3 kilometers an hour. Later on, you had the inflated balloon, like the Zeppelin, that started to take people across the Atlantic. And this incident of the Hindenburg, as you know, is very famous and got hydrogen his reputation as one of the most dangerous things we can deal with. Jules Verne in 1874 already could see the limit of coals and was already calling for a water economy or a hydrogen economy. And where you see what we have today in 2015 with the first hydrogen fuel cell commercial vehicle available on the market, mainly from Toyota. Now there are various competitors on the market. Typically what you have in that car is the same thing as what de Rivaz thought about. It's a balloon, but made of composite material. So you can actually put more hydrogen in that balloon and you can compress the hydrogen at 700 bar. Okay, so this calls a critical question. What are the different states of hydrogen, and can we have access to hydrogen in different forms? Here is something that is called a phase diagram. So typically what this graph is showing you is the different form of hydrogen under different conditions of temperature and pressure. At room temperature and atmospheric pressure, hydrogen is a gas. So typically we are here, and hydrogen is a gas. If you start cooling down the hydrogen to minus 250 degrees C, you will have hydrogen in a liquid form.
Sure, but first you'll have to unlock your device.
And if you want to solidify hydrogen, you will have to go to extremely low temperature and extremely low pressure. And if you want to have hydrogen in a metallic form, again, you will have to go to extremely high pressure. And this has been demonstrated only a few years ago. You can compress hydrogen to densify this hydrogen. So you can use it, for example, in vehicle application. And you may have seen that the norm today is 700 bar. There is a reason for that. It's because as soon as you start compressing more the hydrogen, you need materials and vessel wall thickness that are heavier. And this means that you are going through a curve like this. So at some point, the vessel is too heavy. The volumetric density of the vessel is too low. And so the optimum with the best material we know today is around 700 bar. And so compressing hydrogen at a much higher pressure doesn't bring any benefit. You can also liquefy hydrogen. So typically what you will do is you need to start from very pure hydrogen. Otherwise you are going to liquefy impurities as oxygen and nitrogen also. And then you will run that through a range of heat exchanger, cooling down the hydrogen, for example, with liquid nitrogen first, run that through catalytic exchanger to further liquefy the hydrogen. The reason you need to run the hydrogen through a catalytic system. So a catalytic system is typically a metal that is going to enable you to convert two forms of hydrogen into one. Without going too much into the scientific detail, hydrogen at atmospheric pressure and room temperature exists in two forms, what we call the ortho and what we call the para. And these correspond to the spin. So typically the nucleus or the proton has a spin, which comes from its magnetic moment of rotating. And so as you liquefy hydrogen, you are going to convert all the ortho into para. This is an exothermic reaction. This means it's consuming a lot of energy. And to facilitate that process, you use something that is called a catalyst to do that. And so what you see typically is that the liquefaction process is very energy intensive. And typically 1/3 of the energy is used just to liquefy hydrogen. The energy in hydrogen you put in is used to liquefy hydrogen. So there was a recent project in Europe, Ideal H, that looked at how we can produce hydrogen at scale and at lower cost and reduce that energy input to be able to make this more economically viable. And typically, if you plan to decrease the energy consumption to liquefy hydrogen by a factor 2, you need to improve the efficiency of the heat exchanger, have better catalysts, reduce the pressure drops along the chain, implement new turbine and compressor systems, and most likely then you will be able to reach a $2 or a $2.80 for this liquefaction process of hydrogen. One thing you can do to improve the liquefaction is to use porous material. So is an example of what are called metal organic framework or MOF. And there is a lot of expertise in the country, for example, in making those MOFs. And so what you rely on is material with extremely high surface area. And roughly, there is a rule called the chain rule that you can store 1% of hydrogen per 500 square meter per gram of material surface area. And what this enables you to do is to liquefy hydrogen at a temperature of minus 150 degrees C instead of minus 250 degrees C. But the downside of that is now that you have to use material and you have to find effective ways of producing those materials at cost. So, very quickly, hydrogen is an inert molecule. So if I take hydrogen as a molecule and I try to break it like this, I need a lot of energy. I need around 400 kilojoule per mole. This is equivalent to take an elephant and leave that elephant by a height of 11 meters. So you can see that if you just have pure hydrogen, nothing much will happen. But we show with the Hindenburg, hydrogen can burn pretty well and create some explosion. And so it's very easy to react. For example, if you put it with an oxidizing molecule, oxygen. What will happen is that this hydrogen plus oxygen needs to overcome an energy barrier. So if you just take hydrogen and oxygen and put them together, nothing will happen. But as soon as you provide enough heat and temperature in the range of 500 degrees, those two molecules will be able to cross this, go over this activation barrier for the reaction to happen, and the hydrogen and oxygen are going to react and create water. With that reaction, you will have some energy release, and if this energy release is effectively dissipated within the remaining hydrogen molecule, this will provide additional heat to create a cascade reaction, and so you can have an explosion. One thing you have to keep in mind also is that hydrogen is an invisible flame, so when it burns. So here you have an example of this hydrogen flame, and typically to see it, you need to put, for example, a broom in front, and then you will see the hydrogen burning. So hydrogen flame can be quite something dangerous. So one of the things we have been working on is how we enable safe combustion of hydrogen as a fuel with oxygen. And typically what we are looking at, the kind of things we have been developing is, can we catalyze the reaction? Which means, can we decrease this energy barrier that the hydrogen and oxygen have to overcome to start reacting. And by doing so, can we create the conditions so we cannot have cascade reaction and explosion? So this is an example of the catalyst we are developing. Typical catalysts in the literature that will combust hydrogen. They can combust methane also, that can combust hydrogen as based on noble metal. So we are doing a lot of work to understand how we can develop catalysts that are not based on noble metal like platinum. And so in 2017, we converted some of those catalysts into the shape of barbecues. And so we can claim that we have the world record of cooking pancakes. We cook about 12,000 of them on open day on those barbecues. So let me go a little bit to the science and what has to be tackled. So as I told you, hydrogen exists in an atomic form with a proton and an electron. If you remove that electron, you only have the proton. If you add another electron, you have something that is called a hydride. And then if you bind this hydrogen atom to carbon, you have some hydrocarbons that we use in fossil fuel, but also this is part of our food chain. You can also have some ammonia, and the interest of using ammonia as an energy carrier for hydrogen. You have hydrogen in the form of water, and the idea also to split water to produce hydrogen, and then you will have hydrogen binding to various elements of the periodic table, for example, to chloride to form an acid, or aluminium to form a metal hydride. One thing that needs to be mentioned is that when you look at this hydrogen economy, a lot of those reactions here rely on noble metal and mainly platinum. And so there is a key need to understand how we move away from platinum, which is extremely scarce. Otherwise, we will rely on a platinum economy where we don't have so much resources on the planet of platinum, although we can recycle it. So let me take you through some of my thinking. So around controlling the H plus and the proton, this is a key reaction in fuel cell and electrolyzer. A typical fuel cell is something like this. Typically, you have what we call a bipolar plate that will be there for the gas to diffuse, hydrogen on one side, oxygen, air on the other side. Then you have a gas diffusion layer that will enable a good diffusion of the gases. Then you will have a membrane in the middle that will be there to conduct the proton. As hydrogen comes in, it gets split into its element in proton and electron. The electron takes an external circuit. Then you can use those electrons to create work in the form of electrical work. And then they go back on the other side to recombine with the proton to release oxygen, to react with the proton, and oxygen to release water. Inside the systems, the reactions are quite complex because you have a bundle of activated carbon or various forms of carbon. You have water also that is needed for those protons to migrate. You have catalysts to facilitate the hydrogen splitting, the recombination with the oxygen. And so when you look at a fuel cell and how a fuel cell is behaving in reality, you have the theoretical potential, and then you have activation loss, which means that you will have some loss in the amount of energy you can extract. And this is mainly due to the reaction of the electron with the catalyst to convert the proton oxygen into water or split the hydrogen into proton. You will have ohmic loss, which is mainly due to the internal resistance of the entire device. And so the question is, how do you minimize all those things so you can actually have a cell potential closer to the theoretical value of 1.2 volt? A typical fuel cell in practice looks like this. You have an hafnium membrane, you have a gas diffusion layer, which is a thin piece of porous carbon, and then you assemble that across a bipolar plate. Those ones are made of graphite, and you have one cell, a second one, and a third one, and the entire system forms a stack. So you can end up developing a certain power output. One of the key things about this is, as you can see here, and this is mainly what is happening in industry, also some robotization is occurring now, is that to assemble a stack like this, all this is done by hand. So you need some people that come around and will align everything perfectly. What we are trying to do in my lab is rethink all that. How we remove critical mineral, in particular noble metal, how we increase efficiency, how we extend operability, how we remanufacture fuel cells. So how we assemble all those different elements and we can simply manufacture fuel cells through a very simple technique and method. One of the ideas we have been working on beyond developing very advanced catalysts. So for example, here, catalyst based on tin instead of platinum. We have been working on developing concept around 3D printing fuel cell. So how we can 3D print the entire fuel cell so this can be manufactured in a very effective way and can become a very cost-effective way of making low-power fuel cell for various applications. We have also been trying to understand how we get those fuel cells to work under extreme environment. As I just mentioned to you, a fuel cell will produce some water. This means that in areas where, if you live in Australia, it doesn't really matter. The weather is not often so cold, but if you live in Iceland, it will be sub-zero many days of the year, and so the water inside the fuel cell will be frozen. So how do you develop fuel cells that do not rely so much on water to function? And how do you develop fuel cells that can work around low oxygen content? Because typically what will happen is that if your oxygen content is low and you don't feed the fuel cell with enough air, the catalyst is going to suffer and is going to degrade very quickly. And so we have been working, for example, with Elson Space Engineering to develop fuel cells that can be used to run in high altitude, 40 kilometers above the ground, where oxygen concentration is not high, where it's pretty cold, minus 40 degrees C, how we get fuel cells to power pseudo-satellite to do observation, for example, to monitor bushfires. We have been also rethinking fuel cell architecture, and the reason for that is we want to work toward enabling the use of fuel cell across major consumable goods. So for example, one of the concepts we are working on is cylindrical fuel cell. You will see that across the market and the literature, most of the fuel cells are square because they are easy to manufacture. There are reasons for making cylindrical fuel cell. We can more efficiently remove the water. We can reduce the footprint of those fuel cells, but more importantly, we can start making fuel cell that looks like batteries. So things we are used to. And so one of the concepts we have been working on also is incorporating within those fuel cells a hydrogen storage material. One of the things you may have come across is when you take a fuel cell, you need to inject oxygen air on one side, hydrogen on the other side, and then it will take a certain time for the fuel cell to start. So typically you need to back up the fuel cell with a battery. And the question is how you remove the battery and how you get the fuel cell to start very quickly in few milliseconds, which is what is needed for most power application. And so the concept we have been working on is integrating within that fuel cell a hydrogen storage material. So you actually have hydrogen on board the fuel cell that is stored safely. So this means that you cannot have any thermal runaway or safety runaway. And so when the fuel cell needs to start, the hydrogen is ready to be delivered. You then inject hydrogen gas. The hydrogen gas will diffuse through the hydrogen storage material and get the fuel cell to continue to work. A concept of battery like this that we have been developing and what we call that the hydrogen battery incorporates a solid state material, one of our macro fuel cell, a supercapacitor and a load. And typically, when you look at this, you will have your fuel cell that will produce a current and voltage that are constant across the system. Then you will have the supercapacitor that will deliver a certain peak of power when it's needed. And in that particular example, we use that to run an Internet of Things device that needs to send a message every once a day or so forth to say the temperature in the room is fine or the purity of the water in the system is fine. And the advantage of those systems is then we don't rely on classical electrochemistry anymore, like in batteries. So we rely on macrofuel cell systems that are stable, solid-state hydrogen storage material that are stable. So this means that not only you can increase the energy density compared to a conventional lithium-ion battery, but you can have very long time life for those hydrogen batteries in the field to do what they are supposed to do. Very quickly, we are doing, in particular with my colleague in Japan, similar work around water electrolysis. When you start looking at water electrolysis, you have the alkaline system that rely on the OH reaction. So, but you have also PM electrolyzer, and those are very interesting because not only they are more compact, but they can start faster and they can enable distributed hydrogen generation simply because their footprint is lower. But the downside, again, of such electrolyzer is that they rely on expensive elements, iridium, platinum, and the question is how we remove those from those systems. And so we have been working with my colleagues in Japan, not only to replace those expensive elements. So here is an example with a cobalt catalyst that we have developed, and also rethinking the architecture of those fuel cells, those electrolyzers, sorry. So we don't have problem of bubbles when the hydrogen is generated, and the system can be more efficient. I will stop on that on this. What I want to do now is move to the proton, and those protons are highly important, especially in developing hydrogen storage material. So what is a storage material? Typically, a storage material will store hydrogen in an atomic form. And so this means that you don't store hydrogen as a H molecule anymore, but you store hydrogen as H atomic, which means that you can bring the hydrogen much closer to each other. And this also means that you can store hydrogen in a much more compact fashion than what is possible compared to compressed hydrogen or liquid hydrogen. If you start to look at the energy density, typically hydride will be competitive with fossil fuel because they can store more energy than what you can do with conventional batteries. So there are different types of hydrogen storage materials. There are storage materials that are known today to store hydrogen at the ambient temperature, and there is a range of material we are developing in particular in my lab that store hydrogen at much higher temperature, above 300 degrees C, but they have a storage capacity that is much more higher than what is possible to do with the metallic alloy here in the form of iron titanium, titanium BCC, or high entropy alloys. The way those material works is quite simple. So it follows what we call these equilibrium plateau pressure curves. So as soon as you put hydrogen above the material at a given pressure above that plateau pressure, then you will have hydrogen that diffuse within the material. And then when the material is fully loaded, the pressure will increase. And so this means your material is charged. For the material to discharge hydrogen, you simply need to apply a pressure below this equilibrium plateau pressure, and the material will release this hydrogen. So typically what you see from that is that the way the material is designed will dictate the operating condition and the condition on which, in terms of pressure and temperature, the hydrogen is going to be delivered. Today, we know how to develop those materials with a storage capacity within the 1 to 4 mass percent. And we know how to translate those materials to the market. These rely on discovery that has been done in the 1970s, one from Philips Labs laboratory, where lanthanum nickel 5 was one of the first materials developed to store hydrogen at the ambient. And it was realized that if you tell lanthanum nickel 5, you can simply uptake and release hydrogen. But this material has a poor life cycling. But upon modification, it has been developed and first used in making nickel metal hydride batteries, in which you store hydrogen or you store a proton in the metal alloy. This also relies on the discovery of second alloy based on iron titanium, and this was done in 1974, again in Brookhaven National Laboratory. And you can see this material as what we call two plateau pressure, so it can absorb hydrogen at a certain plateau, and absorb hydrogen at a much higher plateau. And this is not ideal because this means that hydrogen is delivered at different pressure and hydrogen is uptake at different pressure. And so when you look at those materials and how you can control them, and you look at the macrocrystalline structure, you can see that depending on the macrocrystalline structure, you are going to form different phases. For example, titanium or iron titanium, and those different phases are going to be the one detecting how much hydrogen they store. And so you need to develop key knowledge on controlling the macrostructure of the material so you can store sufficient hydrogen. Okay. To develop those materials, you have the periodic table as a playground, and typically what you play with is material that bind hydrogen strongly with material that bind hydrogen weakly. And what you want to do is combine both so you reach the right middle ground so you can uptake and release hydrogen at room temperature, which means that your hydrogen doesn't bind too strongly, but doesn't bind too weakly. And so what you can see from that periodic table is that the composition are infinite. And really what you need to be able to design those materials is to have access to key expertise. And when Peter Annan came to my lab last year, he gave me that funny name of the alchemist. At the beginning, I thought this is a bit silly, but thinking about it when I prepared that presentation, this is exactly what it's about, to be honest. You need to know what you are doing to design those materials. And one material with specific application, specific property can only fit one type of application in terms of hydrogen pressure and release. We implemented those materials a long time ago by designing hydrogen power bicycles. On the side here, you have an hydrogen canister containing a solid state titanium alloy, and this gives a range to the back of 125 kilometers. One of the key aspects when you use those materials is design your storage vessel properly, because when you uptake hydrogen, this is going to generate heat. And the amount of heat you generate is going to slow down the rate of hydrogen uptake. This means that you cannot charge as fast as you want or discharge as fast as you want. So you need to incorporate those materials within your storage vessel in a very effective way. And so behind this, you need to do a fair bit of engineering in your design. In October 2020, we fully developed what we call the world's first prototype residential hydrogen system, where we fully integrated a fuel cell, an electrolyzer, and a hydrogen storage alloy with a storage capacity of 28%. This was designed to take hydrogen at 30 bar from the electrolyzer on board and release hydrogen at 1 bar for the fuel cell on board. And typically, this unit stores the equivalent of 40 kilowatt hour of energy in the form of solid state hydrogen. What I want to go through is that critical map that has been put recently by the European Union, and you can see that if you talk about the renewable energy economy, there are a range of critical minerals that will be needed to sustain that economy. In the interest of time, because I'm running late, one of the key aspects we are working on also is controlling the H-, so the hydride. Beyond the type of material I show you that are ambient alloys, there are a range of very advanced hydrogen storage material with much higher storage capacity that rely on controlling this H- state. And not only this H- state, but this H- mixed with different state of hydrogen. The problem with those materials with higher storage capacity is the temperature at which they release hydrogen. Usually they need 300 degrees C or 500 degrees C to do so. In my lab, we work, for example, with sodium borohydride, which is a typical example. This is releasing hydrogen at 500 degrees C. The hydrogen is not reversible, which means that you cannot get the hydrogen back to reform sodium borohydride. So the key question is, how do we control that reaction so we can effectively store 10% of hydrogen in this material at the ambient? One of the key things and approach we have been working on is developing some precise nanoengineering so we can actually control the structure of those materials at the nanoscale, because we think that if we do so, we will be able to control how strongly the hydrogen binds to the structure. And so we will be able to uptake and release hydrogen at the ambient. And here is an example where we simply evaporate that, stabilize this with a surfactant, and then fully encapsulate that within a nickel shell so we can control the uptake and release from those materials. We can make various nano architecture, and this is a lot of work has been done beyond that by my group to understand how we do that. But the key things is that by controlling the nano architecture, then we can detect at which temperature the hydrogen will come out from that structure. And so if you take an unmodified sodium borohydride and you start to put that in the shape of nanocubes, nanorod, or nanosphere, then you can see that you can shift the different temperature at which you can release the hydrogen from this nanostructure. And so a typical example where you can see that is if, for example, we put that under a macroscope, and here is a core shell structure we have built simply upon the excitation of the electron beam. You can see that this nanostructure is swallowing, and this is because this nanostructure is releasing hydrogen at ambient temperature. And so this is an approach on which we are working at to understand how we can facilitate the uptake and release of hydrogen with those much higher energy storage capacity material. To finish my talk, key things, very advanced front knowledge that we are developing on my lab, I would like to touch upon. And typically these rely on integrating some of the key scientific ideas in the community. So as I told you, typically when you take a hydrogen storage material, the conventional approach is to apply heat. So you can raise the plateau pressure, release hydrogen. When you do that, there is some disadvantages because then you need to have access to a heat exchanger or something like this. And so what we have been working on is, can we rethink that process? So if I take a storage material, put hydrogen pressure on it, put a membrane here that can conduct the proton, and then apply a voltage, I can simply charge my material. And so what we have shown is by simply applying a voltage across our storage material and using a proton conductor membrane here, we can simply charge and discharge the material. And even better, we don't need hydrogen gas anymore. We can simply take water in the form of vapor and typically charge the material from water vapor. The implication of that is, for example, if you think about a refueling station where you have those complicated systems where you need a storage vessel, a vaporizer here if it's liquid, a compressor, a cascade, another compressor to boost and then to be able to dispense the hydrogen, you can simplify all this. You bring hydrogen at low pressure, you bring our new concept in, you bring our new concept in where you simply apply a current or a voltage. You can then charge your car, and in your car, you can simply apply a current and voltage to discharge your hydrogen and get the car up running. Things we have been thinking of also is how we directly use light. Can we directly use light to charge our material? And here is an example where we decorated magnesium nanoparticle with gold, and we use something that is called the plasmonic effect of gold. And by doing things, this and illuminate and shining visible light to our magnesium gold, we can simply uptake and release hydrogen. Even better, what we have shown is that if we take directly something that can help us to split water using photocatalysis, we can directly split water, generate the hydrogen in situ on the material, and then store this hydrogen in our storage material. And for example, we have demonstrated that with titanium nanotubes that are a very good photocatalyst for splitting water, and palladium nanoparticle in this case that we use to store the hydrogen. So if you remember the core shell approach that we are working on, you could think that in the future we could replace this platinum as a storage material by one of our very high capacity core shell material to store this hydrogen in situ. And the implication of that is simply, if you think about what everybody is talking about today, where you have a renewable farm, and then you have electrolyzer on site, and then you have large-scale storage system, whatever the forms, you could shift all that by using a single material that will directly split the water, using sunlight, store it in the material, and this is what you ship. Okay, I would like to finish my talk by talking about climate change, but also societal evolution, and I think it's something very important. And to finish my talk on this, I think hydrogen has a great opportunity to help us with that. Often I see some great ideas around hydrogen, but one of the key things is that we know how to build things like this. They look very nice. There are reasons we don't build them anymore. And so I think we have the opportunity here to develop a new society, and with hydrogen to develop a new economy and do the things the right way, and modernity is in our hands. On this, I would like to thank the teams working with me who are doing all the hard work behind the science, and thank you for your attention.
Thank you, Francois. Look, we don't have much time for questions, but I think the one question that's come through the chat quite a lot is when, in the sense that, at the moment, governments are investing in very large scale batteries to back up solar systems. It seems to be a lot of investment going into batteries at this point. When are we going to see your last picture, the one where that's replaced by hydrogen?
Yeah, good question.
And also, perhaps, what do we need to do to make that happen?
Well, we need some funding. As you know, we need to increase the critical mass. We need to develop the next generation of scientists. We can develop concepts. Taking those concepts to reality takes a lot of effort, takes a lot of focus. And I think this is what we need to be doing in Australia. I know that your office is doing a lot in that space. I think we need to coordinate more to be able to push in the right direction.
But are we talking 2 years, 5 years, 10 years, 15 years? When am I going to see that picture that you showed me as a reality?
We have concept in labs. So let's say this is a TRL 2 or 3. To take that to a TRL 9, we require a lot of investment. We require building critical mass. You are talking 5 to 10 years before you see a real system commercially available.
Okay, so I think someone made the comment about Betamax and VHS. Betamax was the preferred, was a better technology, but never made it because it came too late.
Yeah.
So what I want you to do is work harder. That's what I want, Francois. Okay, I got to thank you. Sorry, we don't have too much time for questions. Thank you very much for a very informative and great talk. And I'm sure my office will have a lot more to do with your work into the future. We normally give you a present at this point, but we'll have to wait till after lockdown to give you the present. And I'd just like to remind people that our next seminar is on Wednesday, the 18th of August, when Professor Hala Zorikwit from the University of Sydney will present the challenge